Okay, this is 5.5, homework help. The first problem says 20% of the radioactive substance decays in 10 years. What percent decays each year? Okay, so our standard form for an exponential equation is y equals a d to the x. Now, we're starting with some amount, I'll call that a. We're going to end with 20% decay, so that'd be 0.8 would be left. So if you start with a, 0.8a would be left. And they want to know how much the substance decays each year. So let's look for the growth rate. And this happens after 10 years. So we're going to put 10 here. We're going to solve for b. These a's will cancel. And so we're solving this equation, b to the 10th equals 0.8. Let's change that into, well, we can take the log of both sides, basically. I usually do natural log because that is the shortest to write. And you can do 10 I'm sorry, I'm solving this the wrong way. What I really want to do is solve for b by taking the 10th root of both sides. So raise 0.8 to the 1/10th power, and that gives you b, which is, so this gives me 0.9779. Now, what I'm going to do, what I'm going to do is do 1 minus this right here, because that's really how much it's decaying. 1 minus the r is really what b is. Or I'm sorry, 1 plus r is what this b is, so I'm going to end up subtracting 1. And you get negative 0.022, which is negative 2.2%. So really it's decaying by 2.2% per year. Okay, so this is going to be the key step right here as well once you find your growth rate. Keep in mind that this, if we're talking about years, this is always 1 plus r. Because what we're multiplying by is 0.97, so we're maintaining 97 or 98-ish% of our amount, but we're losing 2.2%-ish of our amount each year. That's what they asked for. They asked for what percent does the substance decay each year, so I put 2.2% here. And you might want to not round to the 10th. You might want to keep a few more decimal places. Yeah, I would actually keep a few more decimal places there for that one in order for it to work. Okay, the next problem says in 2010 the population of the country was 65 million. So let's just use millions. So we start with 65. Now I'm going to use y equals a b to the x. So we start with 65. That's our starting amount. Our growth rate is 1.8%. So keep in mind that's 1 plus 0.018. So it's really the 1 plus r is our b. Keep in mind. And then raised to some amount of time after 2010 gives us our amount. So in alcohol, I'll use f of t for that because that's what they're using here. And this is what they want us to enter in right here. And you can, obviously make this 1.018. That should work right there. Okay, the next problem says oil leaks from a tank. At t equals 0, there's 220 gallons. So let's use our y equals a b to the x, which is our standard form for exponential. We start with 220. Our growth rate says each hour 4% leaks out. So what that is 1 plus r, where r is negative 0.04. So it's going to be 1 minus 0.04, which is 96.96, or 96%, raised to the t power, where t is in hours. Because if you think about it, we start with 220, and then each hour we multiply by 0.96 because we're retaining 96% of our original amount, or losing 4%, however you want to look at it. So this is what we're going to do. Let's find out how much we end up with after, it says 5 hours. So I'm going to plug in 5 here and find out how much I end up with, and then I'm going to compare that to how much I started with to get the percent of the original that's leaked out. Can we do that real quick? So then if I say, okay, I started with 220, so what did I multiply by to get the 179.38? Divide both sides by this. You end up getting about 0.81537. So that's about 81.5% remains, right? Because this is what we ended up, the overall percentage that remains if we start with 220 and end up with 179. So do 1 minus this percentage, and that gives you the amount that leaked out, which would be 0.1846 or 18.46%. Okay, the next problem wants us to take this formula and use it instead. So instead of y, we use q of t. Instead of a, we'll use q sub 0. And instead of 0.96 or b, we'll use e to the k. All right, so basically what we just need to do is just compare, you know, this e to the k equals 0.96. So set e to the k equals 0.96 and then solve. I would take the natural log of both sides so that you get k equals the natural log of 0.96, which gives you about negative 0.0408. And then what does k tell you about leaking the oil? Select all that apply. So C and F, this is a continuous hourly rate. This is the function we're going to use. I have it on the formula sheet as, I believe, y equals a e to the RT, I'm sorry, P equals e to the RT. I think I have it on there like that. But it doesn't matter what variables you use. Q of T can be A, Q sub 0 can be P. The Webwork's using these variables, that's fine. But this is our continuous compounding formula. And so what that means then is I usually use R instead of K. I don't know why they use K, but that R, in our case, was negative 0.04. It means continually it's decreasing if you do continuous compounding at a rate of about 4%. And so it's continuous hourly rate at which the oil is leaking. And because it's negative, we know that it's decreasing as well. It's positive, it means it's going to be increasing. It's negative, it's going to be decreasing. And this is the same problem with just different numbers. So we can try this one for extra practice if you want, but it's going to be the same process, so I probably won't grade this problem. The next problem says a rubber ball is dropped from a height of 10 feet. So we've got 10 feet here. And each bounce is going to rise to 80% of its value. So 0.8 times 10 is going to give you 8 feet. And so on. So you can see this pattern here. So what we do is write our equation, which is y equals a b to the x. We're starting with 10 feet, and each time we're going to bounce to 80% of the value. So here's our exponential equation that represents that. Now they wanted us to use h of n, so use n as your independent variable and h of n as your dependent variable. And the question is how high will it bounce in the ninth bounce? So the ninth bounce, we're going to plug in 9 for n right here, and that gives would be 1.34. Then the last question, how many bounces before the ball rises no higher than 1 inch? 1 inch, I'm going to plug that in for the y value, which would be 1/12 of a foot. And then just solve for n here, which is the number of bounces. So to solve this, I'm going to divide both sides by 10. So to divide by 10, I'm going to multiply by 1 over 10. It gives me 1 over 120 equals 0.8 to the n. And I'm going to change this into log form, so it's log base 0.8 of 1 over 120 equals n. And I can just do that to my calculator, which would be about 22 bounces, or I got 21.45, so we're going to have to round up the next bounce, 22 bounces. And I missed something key here. It says inches here and here. So what we want is inches, so I'm going to have to start with not 10 feet, because they gave us about 120 inches by converting that 10 feet to inches. And then also when you do this, then plugging in 9, you don't get 1.34, but you get 16.1 about inches. Okay, the next problem says find the half-life of an element that decays by this %. So we're going to fill this formula out, and I want to start with A and end up with half the amount. And my growth rate is 1 minus that 0.03407 to the t power. So what I've done is I filled out my b, which is 1 plus the decay rate per. This is in days, because that's what I'm multiplying by each day to decay. So the question is then becomes, if I solve for this variable, because the a's cancel, what this is answering is how much time or how many days go by where I get half the amount, which is called the half-life. So I'm looking for is this variable here, which gives me the half-life. So I can solve this. These a's cancel, and I get 1/2 equals 1 minus this 0.96593 to the t. And so I can just make this, change it into log form, make it log base 0.96593 of 1/2 equals t, which gives me a t of 19.99, which let's say 20 days. Now it seems to work fine in here. Okay, the next problem says half-life of palladium 100 is 4 days. So we're using the same equation, y equals a b to the x. B is going to be our 1/2, and our exponent is t over 4. The reason why is because when I plug in a 4 here, I know that I've got half the amount remaining. So if you think about it, when you plug in 4, you get a 1 as an exponent, and it's 1/2 the first, so you're multiplying by a half, and you have half the amount. So whenever they give you the half-life, you can always put it here in the denominator of this exponent spot, and put 1/2 as your growth rate. And that will satisfy the conditions that they've given us. And then they say, after 16 days, we're plugging in 16 here, and it's reduced to 7 milligrams, so we'll plug in 7 for Y, and we'll find the initial amount in milligrams that was there. So this will be 7. This is 16 over 4, which ends up being just 4. And we're solving this equation right here. So for A. So I'm going to divide both sides by 1/2 to the 4th power, which is 2 to the 4th power is 16. So I'm going to make this 1 over 16. Instead of dividing by 1 over 16, let's multiply by 16 over 1. So I end up getting 16 times 7, which is 112. Alright, so let's put that there and then go back to the original equation. And this says, what is the mass 5 weeks after the start? Well, 5 weeks, don't enter in 5 here because we set up this equation for days because our half-life was in days. So we have to figure out what 5 weeks is in terms of days, which would be 35 days. So what is the mass 5 weeks after? Well, let's start with the 112. And then let's plug in 35 days for 5 weeks after and solve this equation to find out how much we have left at that time, which gives us about 0.26 milligrams. Okay, the next problem says, here's a function right here that represents the expected score for a student who studies T hours per week. And then K is 0.38, so I've plugged in K, it's 0.38. Now, what you'll find, the first question says, what's the highest score a student can expect? So you could graph this, obviously, and look at the highest score. I think it's, I don't know, it looks something like this. I'm not sure what it looks like, but we can figure this out algebraically, too, because this is 1 over e to the 0.38t here, if I rewrite this. And so you can see if I rewrite it like this, as t gets big, so as you study more and more, if you study like 100 hours, this thing's going to get, this right here is going to get really small and go to 0, because the bottom's getting bigger. So if that's the case, then this drops out, and you just have 1 times 38 plus 61, which gives you a 99%. So the best that you can score if you study, thousands of hours is a 99%. Now, if a student does not study, you put a 0 in here, and then this becomes a 0 power, which we know anything to the 0th power is 1, so this then is 1 minus 1, which is 0, so this cancels out, and we just get a 61. Okay, the next problem, y equals ab to the x is our exponential. It says under ideal conditions, a certain bacteria population doubles, so we're going to put in 2 for b. Every 6 hours, so I'm going to use t divided by 6, so that when I have 6 hours later, I'm doubling it by multiplying by 2. We're going to start with 1,000 bacteria. So here's our function, or I can call that, t, since I'm using t for my independent variable. And what's the size of the population after 18 hours? So we're going to plug in 18 here and solve this, which gives us 8,000. And the population after t hours, I'm just going to enter this in right here. And for the last one, 8,979.696 if you enter in 19 right there. In the next problem, if you start with 16 frogs and you're tripling every 6 days, you put 6 in the denominator here, 3 here, so that after 6 days you have a 1 and you're tripling. Here's our function then. In time to reach 290 frogs, you plug in 290 here and solve for this t by dividing both sides by 16 and then changing this to log base 3 of this number, 219 divided by 16 equals t over 6, and then multiply both sides by 6. And that gives you the answer, which is about 15.82 days, so let's say 16 days. And then just do the same thing we just did in the last problem for 1300. Just plug in 1300 here and solve for this t, which gives you, and they wanted 15.82 and not 16 right there. I don't know why, so be careful about that. Alright, the last problem gives us this, which is the ratio of carbon-14 to carbon-12 t years after an organism dies. So if we have the ratio, we can plug that in and solve for t, or how long it's been dead for. I'm going to multiply both sides by 10 to the 12th, gets rid of this. Now I'm going to change it into log form by doing natural log base e of this, and then multiply both sides by 8,223 and the -1. That gets t by itself, which gives you about 2,701 years.